Welcome to this Forge College Explainer. Okay, so we're officially transitioning out of our previous and, let's be honest, pretty heavy module on Rust memory management. Today, we're diving right into the beautifully logical, visually soothing world of control structures in Solidity. If you've been, wrestling with lifetimes and borrow checkers lately, you are absolutely going to love today's topic. It's a real breath of fresh air. All right, here's the master blueprint for our session today. We'll start with the basic plumbing of Solidity code, move on to gates and flow pipes, check out operators and short circuits, see how guard conditions can rescue our code, look at require, revert, and return, and finally, wrap up all those pipes. So part 1, welcome to Solidity plumbing and leaving Rust behind. Like I said, we're officially in the control structures and functionality module of our Solidity from Zero track. And I promise you, this is going to be an absolute breeze compared to where we just were. Seriously, if your brain is still kind of melting from the introduction to Rust memory management, just take a deep breath. Solidity's branching logic is this incredibly flat, highly logical plumbing system. There are no borrowing rules to fight here. Instead, we're really just directing traffic. Or, for the sake of our minimalist engineering aesthetic today, think of it as directing water flowing through a well-designed system of pipes. The whole foundation of this system is branching, and branching is simply choosing between alternate execution paths based on specific conditions, right? Before you can compose all those complex functions for things like, say, token transfers or checking user balances or strict access control, you absolutely need to understand how to branch your code into different paths based on the rules of your specific smart contract. Which brings us to part 2, gates and flow pipes, our mental model. To truly master branching, you need a solid way to visualize it. I want you to imagine your execution flow as water traveling down a series of literal pipes. In this model, an if statement is essentially a mechanical gate. It's got 2 potential outputs, a true pipe where the water flows if the condition is met, and a false pipe if it's not. It's a very simple binary diversion. Now, when you start combining multiple conditions, you're effectively stacking these mechanical gates left to right in your pipeline. If you have nested if statements, well, the water has to make it through the very first gate just to even reach the second one. And if you use compound expressions, you're basically putting those gates directly in line, right next to each other. Let's look at part 3, operators and short circuits, basically the logic valves of our system. Here are the specific operators that actually control these mechanical gates. We have our logical AND, that's the double ampersand, which requires both sides to be true. Then we have our logical OR, the double pipe, which just needs one side to be true. And finally, the exclamation mark, which simply negates things, flipping true to false. But here's the real secret superpower. The AND and OR operators evaluate strictly from left to right. This gives us something absolutely crucial called short circuit evaluation. Think about it. If the first part of an AND expression evaluates to false, Solidity is smart enough to know that the whole thing can literally never be true, right? So it simply skips the second part entirely because that gate is already permanently blocked. Likewise, if the first part of an OR statement is true, it doesn't even bother checking the rest of the expression. It just lets the flow right on through. Now, why does this actually matter for you? 2 words, gas fees and security. By intentionally putting your cheap, simple checks, like say verifying if a user is the actual owner, upstream, before you do any expensive external contract calls, you're using this short-circuiting behavior to save gas. If the caller isn't the owner, bam, the transaction stops immediately. It's just a brilliant, simple way to drastically reduce your smart contract's attack surface and save your users some hard-earned crypto. All right, part 4, guard conditions rescue, or as I like to call it, fixing spaghetti code. Let's solve a practical engineering problem here to avoid a total plumbing disaster. Just compare these 2 coding styles. Style A is a complete nightmare of nested spaghetti code. You have to read deep into these indented layers just to figure out what's going on. But style B, that uses flat guard conditions. If they aren't authorized, return. If the balance is too low, return. It keeps your main execution path clean, visually beautiful, and most importantly, super easy for a security auditor to actually verify. A guard condition basically acts like a massive bouncer standing right at the entrance of your function. It checks all the preconditions right at the door. That ensures bad data or unauthorized transactions never even get the chance to touch the delicate inner plumbing of your contract. Part 5, require, revert, and return. It's time to choose your exit strategy. So when that bouncer stops someone or a guard condition fails, you have to choose exactly how you want to flush the pipe. I highly recommend systematically following these exact steps whenever you write a function. First, put your constraint checks right at the very top. Next, decide if a failure is critical. If it is a critical error, use require to revert everything. But if a failure just means, hey, nothing to do right now, no harm done, then just use return to gracefully exit the function without triggering a massive error. Keep in mind, this choice has real-world consequences. You want to use require with a really descriptive error string when you absolutely must reject an invalid state and revert the transaction entirely. But remember, a revert still consumes all the gas up to that exact point of failure. Using return avoids the revert entirely, making it absolutely perfect for those optional flows where no critical state changes were actually needed anyway. And finally, Section 6, wrapping up the pipes with some key takeaways. Okay, let's wrap up this engineering blueprint. If you memorize these 3 simple rules, I promise your life as a Solidity developer is going to be so much easier. 1. Put your guard conditions at the very top to fail fast. 2. Exploit short-circuiting to run cheap operations before expensive ones. And 3. Clearly define your exit strategy using require, revert, or return. If you do this, your control flow will be predictable, your logic will stay flat, and your gas fees will be perfectly optimized. So, what's next? You are now fully prepared for our upcoming lesson on loops, where we'll take all this gate logic and apply it to repeating iterations. Thank you so much for joining me for this Forge College Explainer. Make sure you head over to forge.college to dive into that next lesson, continue mastering your Solidity skills, and explore all of our other incredible Web3 topics. See you over there.